Welcome to LR Reports. This channel focuses on institutional research that I've personally reviewed. As a fund manager and family office analyst, my role is to filter through a large volume of research and focus only on what truly matters. AI helps structure and deliver the content efficiently, but the selection and interpretation are human.
Welcome to The Critique. Today we're taking a look at Deutsche Bank's research from January 2026. It's the Data Centers in Space Part 2 note.
Right, the one that models out the economics using feedback from Planet Labs and some cost data from Varda Space.
That's the one. It's a heavy document. It really tries to move the conversation from, science fiction to actual accounting.
It does, but let's start with the most foundational assumption, which is the competition, the ground game.
Exactly. The first major area for improvement, I think, is right there in the comparative baseline. Let's call it the terrestrial constant.
You're talking about the assumption that costs on Earth are basically frozen in time?
Precisely. The core weakness in this entire long-term model is that they assume terrestrial data center costs just sit there, static, at about $16 billion per gigawatt for the next decade.
That's a huge assumption.
It is. By fixing the denominator, they make the path to space parity look artificially smooth. It's like they're assuming space tech will be sprinting while, terrestrial energy and cooling just stand still.
Which is a significant blind spot. I mean, we're seeing massive capital flowing into small modular reactors, SMRs, and even fusion pilot programs right now.
Of course.
If the cost of power on the ground drops by 30% in the next decade, or if permitting reform actually speeds up, that $16 billion baseline just drops.
It falls away.
And that would push the intersection point for space parity much, much further out, wouldn't it?
It pushes the goalposts back just as the ball is in the air. So the suggestion here is pretty clear. They need to introduce a dynamic variable for terrestrial costs.
Not a static constant.
No, you need to model a terrestrial efficiency curve that runs in parallel to the space cost curve. You have to show a fair fight.
That would make the model much more robust. So can we give them a concrete example of how to show that?
I think the best way is a sensitivity table. You add a row that asks the question, if terrestrial capex drops to 12 billion per gigawatt because of a nuclear breakthrough, does space parity shift from 2032 to, say, 2038?
That gives the investor a hedged timeline. It respects innovation happening on both sides of the atmosphere.
Exactly. Okay, so that sets the stage for the economic battle. Now let's move over to the engineering validation. The report spends a lot of time on orbit selection.
Right. The Dawn-Sun synchronous orbit. 600 to 800 kilometers up.
And it's a smart choice. That 98% sunlight fraction is key for power. But there's a structural weakness in how they present the thermal management solution alongside that.
They just say larger radiators, right? To handle the jump from 30 kilowatts to over 100.
Right. And the weakness is that larger radiators is presented as if it's a trivial scaling issue. It completely ignores the cascading penalties for aerodynamics and mass.
Ah, because even at 600 kilometers, there's still some residual atmospheric drag.
There is, and drag is proportional to surface area. So if you triple your radiator size to cool a GPU cluster, you've just turned your satellite into a giant sail.
And more drag means more propellant for station keeping, which means more launch mass, which hurts the unit economics we just talked about. It's a spiral.
It's a nasty spiral. The suggestion is to explicitly link the thermal solution to the propulsion budget. You can't just wave a hand at cooling without paying for it in fuel.
So what's the fix here? How do they tighten that up?
Well, a concrete example would be to reference specific emerging tech. Things like deployable membrane radiators or two-phase mechanically pumped loops. And then you estimate their mass penalty in the different satellite models.
So you show the actual calculation.
Yes, show the math. Increasing thermal dissipation to 100 kilowatts increases the drag coefficient by X, which requires Y% more Hall thruster fuel per year. That shows you actually understand the physics, not just the concept.
Okay, let's stick with the physics, but move to the speed as an asset argument. The report makes a big deal about contrasting rapid satellite production, Starlink building 10 a day, with the slow permitting for terrestrial data centers.
It's a really compelling narrative hook, but it lacks a critical counterweight. The weakness is that the report sort of treats space as this wild west of infinite speed, and it dismisses the rising tide of orbital regulation.
They do mention traffic management is factored in, but with 100,000 satellites projected up there, the FCC and the ITU are getting much more aggressive.
Correct. Just because you can build 10 satellites a day doesn't mean you'll have a license to launch and operate them at that cadence forever. The suggestion is to treat orbital permitting risk as its own distinct variable.
Similar to terrestrial permitting.
Exactly. It feels like they're just trading one bureaucracy for another.
Yeah, they are.
So a concrete improvement would be to add a regulatory risk premium to the OpEx line in the model. Maybe you increase the OpEx assumption from 1% to 2% specifically to account for compliance delays, collision avoidance, potential debris taxes, all the stuff that's probably coming by the 2030s.
Speaking of OpEx, let's drill into that number. The model lists operation cost at just 1% per year.
Yeah, this is one of the most fragile assumptions in the entire spreadsheet. The weakness is that a 1% OpEx rate, I think, wildly underestimates the harsh reality of managing a constellation of 10,000 flying GPUs in a radiation environment.
Absolutely. On Earth, if a server fan breaks, a technician just walks down the aisle and swaps it out. In space, that whole asset is it's dead.
It's gone. And the report kind of conflates maintenance with depreciation. The suggestion is to separate maintenance OpEx, the cost of the team on the ground flying the birds, from revenue lost due to degradation.
That's a crucial distinction. It's not just that it costs money to fix things you can't touch. It's that the asset itself generates less money over its lifespan.
That's it. So a concrete example for improvement is to model a performance degradation curve. Assume, for instance, that radiation bit flips or thermal throttling reduces your compute capacity by 20% over a 3-year lifespan.
Which effectively raises the price per compute cycle for the end customer.
Right. Showing that degradation makes the revenue model much more believable than just a flat 1% maintenance line.
Okay, let's pivot to launch economics. This is the primary driver of the whole thesis, right? Dropping from a 7.2x premium down to 1.5x.
The entire model really hangs on the Starship variable. They model a cost drop from, $1,600 per kilogram on a Falcon 9 to under $70 a kilo on a mature Starship.
That $70 figure is the holy grail. But isn't relying on that single number a huge vulnerability in the analysis?
It is. The weakest is the binary nature of that assumption. It frames the future as either status quo or Elon's best-case scenario. There's no middle ground modeled.
Nothing for a world where Starship works, but maybe it's operationally complex and settles at a higher price point.
Exactly. So we need a stress test. The suggestion is to stress test the model against a Starship moderate scenario. What happens if launch costs actually settle at $200, maybe $300 a kilo because refurbishment is harder than they think?
That would change the ROI calculation dramatically.
It does. A concrete improvement is to explicitly state the break-even launch cost. Add a line right in the executive summary that says, this entire model remains viable only if launch costs stay below, say, $350 per kilogram.
That gives the investor a clear kill switch metric to watch. It's not just a hopeful target.
Right. Let's talk about the workload itself. The report distinguishes between training, which they say is invalid for space, and inference, which is valid.
And they make the right call there. Processing data where you create it, in orbit, that just makes sense.
It does, but they lean really heavily on the latency argument. They claim space-to-ground can be faster than fiber.
Well, because light travels about 40% faster in a vacuum than in glass fiber. Physics is on their side.
Physics, yes. Geometry, no. The weakness here is that this low latency benefit is transient. It's highly conditional on the constellation's density. A LEO satellite is only directly overhead for a few minutes.
So if the satellite isn't overhead, the signal has to hop through the mesh, which adds latency.
Correct. The suggestion is to temper the latency argument by quantifying what that density requirement actually is. Don't just say it's faster. Tell us what it takes to make it faster, consistently.
That's a good challenge. So how would they even calculate that?
A concrete example would be to calculate the minimum viable constellation for specific low latency guarantees. State it clearly, something like, to beat fiber latency 99% of the time between New York and London, this constellation needs a minimum of 4,000 satellites.
Right. Putting a hard number on the density ties that marketing pitch back to the massive CapEx reality.
Exactly. Building on that connectivity piece, let's look at the optical laser terminals. The report correctly identifies this as a supply chain bottleneck.
Yeah, it's a strong reality check. They note the tech exists. They cite the Starlink mini laser, but that the merchant supply chain just doesn't have the scale.
And they mention that a company like Planet Labs might have to build this capability in-house.
Which sounds...
That sounds insanely risky.
It's a huge execution risk disguised as a minor pivot. The weakness is treating the in-house development of optical terminals as some operational detail. It's not. It's a fundamental change in the company's entire risk profile. Vertical integration is expensive, and it is hard.
And hard usually means over budget.
Exactly.
The suggestion is to quantify the make versus buy penalty. If Planet has to become a laser manufacturer, how does that impact their non-recurring engineering spend, their NRE?
Currently, they list cumulative NRE at around $2 billion.
So a concrete improvement would be to show a scenario where that NRE balloons to 3 or 4 billion because of this one component bottleneck. Does the return on invested capital still hold up if they have to burn an extra billion just learning how to build lasers?
An investor needs to know that.
They do. Okay, let's zoom out to the strategic section, the high ground premium.
Right. This is where they argue governments will pay above market rates for space compute because of security and geopolitics, the sovereignty argument.
Which makes sense, but then they kind of veer off into Moon and Mars precursors.
And that's where they lose you.
That's where they lose me. I find the Moon and Mars section to be a distraction.
But it paints the long-term vision, right? Interplanetary internet.
It does, but in a report that's supposed to be focused on the economics of LEO deployment in the next decade, talking about lunar base autonomy just feels like fluff. The weakness is that it dilutes all the hard-nosed financial modeling that came before it. It gives skeptics a reason to roll their eyes and say, see, it is science fiction.
So, cut the Mars talk?
The suggestion is to replace the Mars colonization angle with a much deeper dive on sovereign AI clouds. That is a much more immediate and, frankly, monetizable use case.
Can you expand on what that looks like?
A concrete action is to swap the Mars paragraph for an analysis of which nations might want their data processed in space, specifically to avoid the legal jurisdiction of other countries. Data havens in orbit. That's a real legal and commercial product you can sell in 2028. A Mars base is not.
Keep the focus on the money.
Keep the focus on the money. That's a sharp pivot. Okay, last thing, looking at the report physically. The layout, the data presentation. Figure 2 is the sensitivity analysis.
It's just a dense wall of numbers.
It is. The weakness is it forces the reader to do all the mental math to find the parity line. You know, the point where space becomes cheaper than Earth.
It's just rows and columns of costs. You have to hunt for it.
The suggestion is to visualize this graphically. Make it a zone of profitability. Don't make the investor squint.
Like a heat map?
Exactly, like a heat map. A concrete example. Shade the cells green where space is cheaper than Earth, red where it's more expensive. Make it instantly visual that at $1,600 a kilo launch cost, the entire board is red. But at $200 a kilo, a green zone starts to open up in the bottom right.
Visualizing the frontier of viability makes the whole thing actionable at a glance.
It does. Okay, one final point. On the timeline, the report concludes that parity arrives in the 2030s.
Which is...
Too loose.
It's way too loose. The 2030s is a 10-year window. For an investor, 2031 is a huge opportunity. 2039 is a disaster.
So, is it just a lack of conviction?
I think it's a lack of milestone mapping. The weakness is the vagueness of that convergence point. So the suggestion is to tie the date to an external catalyst, specifically the Starship mature date.
So instead of a calendar year, you use an event horizon.
Correct. A concrete example would be to phrase the prediction like this. Cost parity is achieved 36 months after Starship achieves a weekly launch cadence. This ties the whole prediction to an observable, trackable metric in the real world, not just a generic decade. That grounds all the speculation back in reality.
Exactly. So let's wrap this up. A synthesis of our critique for the authors at Deutsche Bank.
Let's do it.
To the research team, this is a high-quality, very provocative piece of work. It elevates the discussion. But to make it bulletproof, we have 5 key takeaways. First, fix the terrestrial constant. You have to introduce a sensitivity variable for falling energy costs on the ground. Don't assume the competition will sleep.
Second, get real about thermal management. You need to be specific about the mass and drag penalties. Show the trade-off between keeping chips cool and the fuel needed to stay in orbit.
Third, quantify the latency argument. Don't just say it's faster. Calculate the minimum viable constellation density needed to consistently beat fiber.
Fourth, sharpen that high ground strategy. Cut the Mars colonization fluff and focus on sovereign AI and jurisdictional immunity. That's the near-term premium driver.
And finally, visualize the data. Turn that sensitivity table into a heat map. Clearly define the zone of profitability so an investor can see the path to parity instantly.
And I'll reiterate my point. Add that regulatory risk premium. The days of the Wild West in LEO are ending fast.
Agreed. With those adjustments, this report moves from being a theoretical exploration to a definitive investment roadmap. We'd love to see the V2 model once some of that first prototype data comes back in 2027.
Absolutely.
That's it for this critique. Now, get back to work.
That's how we approach research internally. Filter first, then analyze, and only then decide what's worth sharing. If you find this useful, feel free to follow the channel. I'll see you in the next episode.